My name is Chris McCall. I'm talking about the Unit 2 case connections. The first case that I chose to do was the case number 1. It states pyruvate kinase, PK, catalyzes the rate-limiting ATP generating step of glycolysis in which phosphophenoPyruvate, or PEP, is converted to pyruvate. Multiple isoenzymes of pyruvate kinase exist in mammals. Type L, which is found in the liver and kidneys. Type R, which is expressed in erythrocytes. Type M1, which is found in tissues such as the brain, and type 2, which is present in self-renewing cells such as embryonic and adult stem cells. Under normal conditions, describe all the ways in which pyruvate kinase is regulated in the cell. And my response to that is there are 4 pyruvate kinases in the mammalian body, as previously stated: PKM1, PKM2, PKL, PKR. They can be regulated allosterically or through phosphorylation. Fructose 1,6-bisphosphate, or FBP, allosterically activates pyruvate kinase. The more FBP, the more glycolysis can happen. FBP is a feed-forward activation that helps the end goal of energy production. Now, this is one of the only feed-forward activations that the human body has. High ATP levels reduce enzyme activity. Obviously, that's true if you have a bunch of energy stored. Why would you need to make more? So if there's a high level of ATP, you do not have to make more ATP, so it regulates it to reduce the enzyme activity. Alanine regulates pyruvate kinase because it will divert to making glycogen. When the body has a lot of energy, the body will likely switch to making energy to storing energy in the compound glycogen. Glucagon-mediated phosphorylation inactivates in the fed state due to phosphorylation of the PK enzyme. This also stimulates gluconeogenesis because the high levels of blood glucose. So glucagon will phosphorylate and inactivate the glycolysis process, so that we stop making pyruvate and we start diverting pyruvate back to new glucose. And then there was a second part of this as well. It says many types of cancer cells are predominantly glycolytic and overexpress ONC protein MYC. Interestingly, the classic ONC protein MYC has been found to promote preferential expression of pyruvate kinase type M2 over pyruvate kinase type M1. The isoform is characteristically found in low activity state and is ineffective at promoting glycolysis when compared to pyruvate kinase type L or type 1. The logic seems counterintuitive for glycolytic tissue. What is the relationship for this mechanism, and what are the pathways, or what other pathways may cancer cells be diverting substrate to? And for this one, I had to do a little bit of research, not only in the book but as well as on the internet. PKM2 is preferential for tumors because it has increased production of macromolecules such as amino acids and nucleic acids through the pentose phosphate pathway. This allows allosteric enzymatic activity without the accumulation of reactive oxygen species. So when the pentose phosphate pathway produces NADPH, it suppresses the amount of reactive oxygen species. The onc-protein helps keep PMK2 or pyruvate kinase M2 at a lower activity state. Without this low activity state, the tumor proteins could not divert glycotic products away from glycolysis. As a result, the activity state of the tumor proteins could divert, or as a result, the tumor thrives without needing much glucose because there are other macromolecules and other ways of getting ATP around. This leads to the buildup of proteins, lipids, and nucleic acids. Thus, the tumor has all it needs to survive because the tumor doesn't need to go through glycolysis. It has lipolysis and breaking down amino acids and such. So those are the answers to my case number 1, and then case number 4 is the other case that I chose to do. So when I read the first couple lines of this one, let me read it first. Case 4, a previously healthy 2-month-old female presents with jittery spells several hours after breastfeeding. Her mother reports she has not given the baby anything to eat other than breast milk since birth. The baby has only recently been sleeping for more than 2 hours between feedings, and that's when the mother reports these symptoms started. Laboratory results are consistent with hypoglycemia, but are otherwise unremarkable. Epinephrine is administered, and there is no increase in blood glucose, but there is an increase of blood lactate. Hint: think of the pathways would be activated by this hormone. Physical exam reveals a liver edge 4 centimeters below the right costal margin. Percussion of the right chest and abdomen confirms enlarged liver or hepatomegaly. Blood glucose levels increase after breastfeeding, but she cannot maintain blood glucose levels with a normal range during fasting. Based on the information above, which of the following is most likely diagnosis of the patient? Hereditary fructose intolerance, galactosemia, glycogen storage disease, inability to use glycogen, and then glucose 6-phosphate dehydrogenase deficiency. So like I was saying, when I first read this, I skipped directly to the answers and thought the answer would have been galactosemia because breastfeeding is made up of lactose, which is a derivative of glucose, which is a compound that derives into glucose and galactose. But upon further investigation, the signs and symptoms, I couldn't rule that one out completely. However, the one I could rule out completely was hereditary fructose intolerance. Since the child has been on nothing but a breast milk diet, there is little to no fructose in the breast milk, so that the infant hasn't been introduced to fructose, which would mean there's no basis to think that it would be hereditary glucose intolerance. The remaining 3 answers all result in an enlarged liver. So that part was irrelevant to determining what was ailing the child. The second one I could rule out after a little bit more research was galactosemia. It isn't galactosemia because it doesn't cause high levels of lactate in the blood only when given epinephrine. Lactate in the blood would be there always due to the fact that the lactose can't be broken down properly. So the presentation of galactosemia is also much faster than 2 months. It usually happens within a few days / weeks of birth, so it is a little long for the presentation to just now be addressed. And the other 2 answers are both viable given the symptoms, but the one that stands out above the rest is glycogen storage deficiency. The glucose 6-phosphate dehydrogenase is not as dangerous because it only happens through the pentose phosphate pathway. Then the glycolysis and glycogenolysis pathways. Since epinephrine induces glycogenolysis, or breaking down of glycogen into glucose, assuming that there would be an increase, or you would assume that there would be an increase of glucose in the blood due to the abundance of glucose from the breakdown of glycogen from the liver. However, when the child was administered epinephrine, there was no glycogen storage, so the body resorted to other means of ATP production. If there were an abundance of glucose or glycogen to use, there would be an increase of blood glucose because the epinephrine stimulates glycogenolysis. Other symptoms confirmed, such as enlarged liver, lactic acid buildup in the bloodstream. So for this one, I chose C, glycogen storage deficiency. Those are the two cases I chose, and